Welcome everyone to the final talk in our first session of MACSMIN conference. It's a great pleasure to introduce Professor Graeme Day, who will talk about molecular crystal energy landscape analysis using the threshold algorithm. Over to you, Graeme, please.
Okay, thank you, Vitaly. Thanks for inviting me to talk. I enjoyed last year's conference where I gave a bit of an introduction to molecular crystal structure prediction. And today I'm speaking about some work we've done in the last year to sort of add on to those methods, which I hope will be interesting. I should say up front, all of this work has been done by a great PhD student who's just finishing up, Bruce Yang, in my group. So just to very quickly reintroduce crystal structure prediction, the idea is that we have computational methods which take us from a two-dimensional picture of our molecule and having nothing else beyond this able to get to the landscape of possible crystal structures that this molecule could adopt. The way we do this is we initially have to take a two-dimensional diagram of our molecule and inflate this to a three-dimensional building block of our crystal structures. And we use sort of conformational searching methods for this. We will say rotate dihedral angles in the molecule and any other flexible degrees of freedom to come up with how that molecule might look in terms of a three-dimensional object. And then for each stable molecular conformer, we then go through a packing process. The types of methods we use here, I won't go through them today. We use low discrepancy searching, which just means generating trial crystal structures as uniformly as possible across our degrees of freedom. And those degrees of freedom correspond to the unit cell, which dictates our translational symmetry. So the lengths and angles of our unit cell, as well as how the molecules are positioned within the unit cell, orientations and positions of molecules, and potentially sampling again the intramolecular degrees of freedom. So it's a very high dimensional energy surface, and essentially we're looking for all of the local energy minima on this surface. This usually requires us to be sampling on the order of at least tens of thousands, but usually more towards hundreds of thousands, potentially millions of trial crystal structures, which initially are not at minima on the energy surface. So then we apply some energy minimization to these. And you often see things then summarized on a very simple plot like this, where we have energy and density or some other structural parameter, and each point on this plot corresponds to a distinct crystal structure which has been generated and energy minimized in the computer. The assumption being that the lowest energy structures on this landscape will be the most likely to be observed experimentally. In this case, I show you, of course, a nice example where this works out. For this molecule here, in red is our global energy minimum predicted structure, and that's overlaid with the structure you get from X-ray crystallography, okay, in green. And you can see the agreement here is quite good. And if we can get agreement that well, then we can go on and predict properties, and this can be useful for, say, guiding an experimental screen for materials. I should also say this is not just a global optimization problem. We're not just interested in the global minimum. We're also interested in the slightly higher energy structures because these can correspond to polymorphs, where that molecule crystallizes in more than one potential packing, or to take into account errors in our energy methods as well. We can't just focus on the global energy minimum. So we're interested in methods which get us this whole ensemble of potential crystal structures. And just to put sort of those energy landscapes in context, we did this work, it's a while ago now, but where we took lots of experimentally observed polymorphs of organic molecules. So this is where we have at least two crystal structures of an organic molecule, and we calculated the energy differences between them. And these often turn out to be very small. In over half of cases, it's less than 2 kilojoules per mole. And in 95% of cases, it's less than 7.2 kilojoules per mole. So these energy differences tend to be small, And that sort of tells us where to focus on these energy landscapes once we have predicted them in terms of looking for potentially observable crystal structures. Now, we often do, and I've been referring to this as the crystal energy landscape. It's not actually a term that, from what I've been speaking about, I think we should be using. If you think about what we mean when we talk about a landscape in more general usage outside of crystal structure prediction, then we're talking about sort of the whole picture. Say, thinking about this mountain range in this picture here. When we describe the landscape, we're not just talking about the local minima, so the points where you might sit comfortably in valleys on this hillside, but the landscape should describe as well the pathways between these, and so how difficult it is to transfer from one valley to another, because that can also be important in terms of interpreting these crystal structure landscapes that we generate. In the crystal structure prediction literature, crystal energy landscape is increasingly being used to talk about just this set of local minima. And we're trying to augment on that. And that's what I'm going to be talking about today. So we're trying to get an idea more about sort of the barriers between these. Ideally, we would also know a bit about the pathways, okay? So that we can talk about this whole landscape of our crystal structure corresponding to a given molecule. So this is where the threshold algorithm comes in. There are lots of ways of trying to sample transitions between structures. This is what we've taken to initially use to try to do some of this work. We haven't invented this threshold algorithm. Sean and Putz and Janssen described this well, quite a while ago now, and it's a method which I'll now describe and how we're doing this. So we take a starting structure, which would be a molecular crystal, perhaps from this crystal structure prediction procedure that I've described. So we're at a local minimum on our energy surface. I'm drawing this as one-dimensional structure, whereas in reality, this captures all of those structural dimensions I'm talking about. So usually at least 12 dimensions, often higher towards about 20-dimensional energy landscape. And our vertical dimension is energy. So we're in this little basin. We start from a structure which we've predicted. And what we start to do is some Monte Carlo sampling. So we take that structure and we allow some small changes to the structure. So random moves of the molecules in the unit cell, or translations, or maybe small changes to the unit cell itself. Okay. And what we do is we allow this distortion of our structure as long as it leads to an energy change which sits below a lid. Okay, so we apply a strict lid on this, and any move that gets applied in Monte Carlo sampling which goes above that lid gets rejected. Anything below gets accepted. So we're allowing ourselves at this stage, when the lid is low, to be just sampling locally around that energy minimum. And then what we start to do is we increase that lid. All right, and as we increase the lid, then we start to allow Monte Carlo moves within a wider range around that minimum. You see that a little bit of the other landscape has appeared over here in terms of visualization. We can't get to that yet, okay? Because we're only allowing moves which go within here, within this basin, okay? We will only be able to see that energy minimum when the lid starts to get to the point where it goes above the energy barrier that connects these two minima. Okay, so you can see where this is going. We'll keep increasing that lid. We're still in this isolated local minimum. But at this point, the lid energy is increased to a certain point where accepted moves, distortions of our structure, will be allowed to move over to this other neighboring energy basin. Okay, so as long as we can identify what basin our structure belongs to at any point along this trajectory, then what this allows us to do is it tells us roughly where that energy barrier is. The lowest energy lid at which we get a connection between two minima gives us an approximation of the energy barrier. We're always going to be overestimating energy barriers using this method. A nice thing about the method is we are not having to calculate anything like derivatives at our energy surface, which would be required for other types of transition state searching methods. Okay, so we start to get connections, and as this lid goes up and up and up, we get more and more connections between minima on an energy landscape, or connections between those predicted crystal structures. Okay, and what I'm drawing here in dashed horizontal lines are all of those points where lid energies have allowed new connections between energy minima. And it can get quite complex because we're in a very high dimensional space with lots and lots of local minima. So you can see sort of how this goes. This is for one of the first molecular crystals we applied this to. We increase the lid here in increments of 5 kilojoules per mole, and we're allowing sort of thousands of potential steps before we increase the lid to the next lid energy level. And these green points are where we get to in terms of energies, what gets accepted. That keeps creeping up and up and up. And the blue points are currently what we have to do to identify what minimum we're sitting in is to locally energy minimize either all of these structures or at sort of increments along our trajectory. We energy minimize structures to see what local minimum we're sitting in, and that allows us to identify when we have those connections. Okay. Now, as I said, it gets quite complex to stare at these things and look at the connections. So one thing we use is what's called a disconnectivity graph. And it's just another way of looking at this energy surface. So on the left, we have the energy surface simplified to this one dimension. On the right is the corresponding disconnectivity graph. So all we need to do to draw this is every time we get a connection, say between this minimum and this minimum, then the lines which correspond, so the ends of these lines correspond to those local minima, and where those meet corresponds to the lid energy at which those are connected. Okay, so it's called a disconnectivity graph because if I go from the top to the bottom and sort of lower my threshold, then this ensemble of structures gets more and more disconnected until you get to the point where all of the structures are disconnected. Okay, but the structure of this disconnectivity graph we found can be quite useful for then characterizing the landscape of crystal structures that we have. So I'm going to go through a few examples of what we've tried out with this method. We've only sort of had it for the last half year or so, so we haven't done much with it, but we've been sort of testing out how it works, some of the limitations of the method as well. So initially we started to look for polymorphs of organic molecules, which sat in the same space group symmetry, because this allows us to apply some constraints on the sampling. Because one problem we have when we do this sampling and the threshold method is we need to apply very small perturbations to our crystal structures. If we allow large perturbations, we have a danger that we hop over or through an energy barrier, even though we have the lid there. Okay, so we need to be applying very small perturbations, and that limits our sampling. So if we can reduce the dimensionality of the search, that really helps us. Applying space group symmetry is an obvious way to do that. So initially we looked at this indigo system. It has 2 polymorphs. Okay, it has some nice hydrogen bonding as well. This is how the molecule hydrogen bonds into initially chains, but these chains connect into 2-dimensional layers, which I'm trying to show in the bottom picture here. We picked this system because although it has 2 polymorphs, the hydrogen bonding is constant between those 2 polymorphs. So it has these 2 polymorphs, A and B, and I'm overlaying them here in blue and gold. Okay, and you can see that one of those 2-dimensional layers overlays very nicely between the 2, and the only difference we have between A and B is that we have an offset of the layers, the second layer. Okay, so we chose this system because 1, they're in the same space group symmetry, and 2, we expected because there isn't a requirement to break any hydrogen bonds, then we might get a low energy connection between the local minima corresponding to these structures. And so we applied the threshold algorithm. So these structures could be described, well, in the real symmetry has half a molecule in the asymmetric unit for each of these crystal structures in space group P21 upon C. We need whole molecules when we're doing things so that we can have free translation of molecules during sampling. So we took a subgroup and we initially did calculations in P21 with a whole molecule in the asymmetric unit. We started just 2 trajectories from the crystal structure prediction points, and I'll show you the crystal structure prediction plot in a minute, but we started from those points which correspond to polymorphs A and B. They get reproduced quite nicely by the CSP methods. And so we started trajectory from each of those. We increased the lid in 5 kilojoule per mole increments initially with 1,000 steps per increment. And we keep going until everything's connected. Okay, and this is the disconnectivity graph that we get for indigo. So you can see I've labeled the 2 gold points here, which are our starting positions. And so you can see a few things here. The first connection between A and B comes when the lid is about 30 kilojoules per mole above the lowest energy point, which is polymorph B. There is one other structure that gets connected to A at a smaller barrier, and two other structures here and here, which get connected to A and B at that same lid energy that A and B meet. Okay, so you have sort of a super basin on your energy landscape, which contains 5 crystal structures, which are connected at energies below 30 kilojoules per mole in terms of the barriers between them. If you visualize all of these, they all have the same two-dimensional hydrogen bonding that overlays perfectly. The only difference you see is different arrangements of those layers on top of each other. So relatively small energy barriers, because all you have are these changes in the stacking and aromatic interactions. Okay, no other structures get connected to this set of 5 for another 15 kilojoules per mole, and then you start to get other structures on your landscape. Okay, so this gives quite a nice picture of our energy landscape as sort of a single funnel towards this set of 5 crystal structures, all with a consistent hydrogen bonding, of which the known polymorphs A and B are the lowest energy structures. Okay, so it's quite nice insight that we don't have just from the crystal structure prediction, which told us nothing about those energy barriers. Here is that crystal structure prediction plot, so we can now sort of map that information on. So those are those 5 structures, and they appear in that lowest energy region of our crystal structure prediction plot. Okay. So we can sort of characterize things in terms of basins. This is not so interesting because everything sort of sits in one basin, so we don't get so much extra information that we can put onto this CSP plot. Okay, but that was our initial thing that we looked at. Something we were a bit worried about was the results or the errors which might be introduced by applying symmetry. So when we were applying symmetry in these Monte Carlo perturbations to the structure, it means that we only had to be moving one molecule, and the other molecule moves to maintain the space group symmetry. So we've lowered the dimensionality by having 6 degrees of freedom for one molecule instead of 12 for 2 molecules in the unit cell. Now, these 2 polymorphs could also be described in a bigger unit cell containing 4 molecules with space group symmetry P1 upon C. So we just decided to repeat the calculations with this. And here's the disconnectivity graph you get from those simulations. Now, it has many more local minima on it, which tells you that in this larger unit cell, you can hit more local minima. But the overall qualitative picture has not changed so much. We still have this funnel which goes down to A and B. Okay, they sit in the same funnel, they're connected to each other, but the connection between them drops quite a bit. You're in a bigger unit cell, it seems there's more freedom for a lower energy transition between those 2 polymorphs in this larger unit cell, although you still have symmetry relations between all molecules in the unit cell. This energy barrier is dropped from 30 to 15 kilojoules per mole, and what that does is it means the energy barrier between the 2 known polymorphs is now lower than the barrier to any other polymorph, any other predicted structures, unlike what we had in the initial simulations in the smaller unit cell. So there are effects of the space group symmetry constraints that we put on these searches. And that's just really summarizing what I've just said there. But qualitatively, it doesn't seem to change the picture, but it does give quantitative differences, as you see. So we moved on now to some other systems. We chose this one here, which is a co-crystal between nicotinamide, this molecule here, and benzoic acid. Again, we chose this one because it has 2 characterized polymorphs, which again have the same symmetry. So we're not taking the step yet to relax our symmetry constraint because it's already quite a complex system because it has 2 molecules which have to be moved independently. The other interesting thing, and the reason I show this one, is to contrast to the indigo case, because here the 2 polymorphs, although they're very close in energy, they're separated by less than a kilojoule per mole in calculated energy. The difference structurally between them is much greater. There's a big change in the hydrogen bonding connection, which is going to be the strongest intermolecular interactions holding these crystals together. So here you have nicotinamide, double hydrogen bonds, and these benzoic acids sort of linking these dimers of nicotinamides. And essentially most of those hydrogen bonds would have to be broken to then get to this arrangement here where you have nicotinamide chains with the benzoic acid sitting off each nicotinamide here. Okay, so a big change that's required. We wanted to see what the impact of that was on our picture of the energy landscape. So we sampled this. They're both in space group P21 upon C with a single pair of molecules in the asymmetric unit. So we had to, because we have more dimensions, because of having two molecules, we apply larger sampling under each energy lid, but we stuck to a 5 kilojoule per mole increments. That just sort of limits the precision which we can get these barriers characterized. And this is the landscape we get. So a very different picture from indigo, in that here is our starting point for polymorph 1, starting point for polymorph 2, and they sit in completely different funnels on the energy landscape. Okay, so it's very different from what we saw for indigo. The sampling does find a connection between them. So we're happy with that we have sufficient sampling that eventually the connection is found between 1 and 2. And by a connection, the way we look for these is we analyze the trajectory that starts from 1, and we analyze the trajectory which starts from 2. And if a common local minimum is found in those trajectories at a certain energy lid, it means that those trajectories are connected at that lid. So that's how we go about things. So it does require good methods for identifying when we have identical crystal structures. Okay. But it takes us all the way up to 120 kilojoules per mole above our starting structures before we get that connection. So compare that to the 15 kilojoules per mole that we found for indigo. It's a very different energy landscape, but you can see there are lots of structures which are connected by lower energy barriers to each of these polymorphs. Okay, so within each of those funnels, there's a lot of detail. Contrast that to the picture you get from just looking at that energy density diagram, which is usually the way that we look at things in crystal structure prediction. This is that energy density diagram for this co-crystal. Okay? The two observed polymorphs sit not at the global energy minimum, but down here as these 2 points. So very low on that energy landscape. But all of the points, all of the predicted crystal structures sort of sit in a big blob in energy density space. And if you plot the structures which sit in funnels 2 and 1, here as green crosses and these red bars, then you can see that they just sit in the same region of energy density space. So they overlap each other in this projection of the energy landscape we get. And that's how people have been looking at crystal structure prediction results for decades now. Okay, we're losing a lot of information. The fact that these structures sit, or these groups of structures sit in different funnels on the energy landscape, and that can relate then to, say, kinetics of transformation between these. In this case, these two polymorphs, although one is more stable than the other, these can be sat for months on the bench and they won't transform between each other. Whereas if you had lower energy barrier between them, then you might eventually get transition to the lower energy form. Okay. So that's just, again, summarizing some of those points that I made. We're getting a lot more information, and I prefer now this visualization of energy landscapes to the traditional one, which we've been looking at for many years. So contrasting those again, indigo, where we have this low barrier between the two known polymorphs, versus this co-crystal here, where we have these very separate funnels, and it gives you a picture of very different crystal systems. We do need to start moving towards removing those symmetry constraints, because by applying symmetry to the allowed perturbations of our molecules within our crystals, we're limiting the types of transitions, and that might be overestimating barriers between structures. There may be lower energy barriers if we could allow things to move without constraints. So then we moved on to some other, still fairly simple systems, but where we need to remove those symmetry constraints. So one that we looked at was tetralic acid. And tetralic acid, these are the two known polymorphs, alpha and beta. They sit in different space group symmetries. So this one, alpha, space group P1 bar, so it just has inversion centers relating molecules, whereas beta polymorph has screw axes. Okay, so if you applied inversion centers to your sampling, you would never be able to get from alpha to beta. Okay, so we need to now do the calculations with no space group symmetry constraints. The other interesting thing about tetralic acid is it's another system where we have a change in hydrogen bonding connectivity between the polymorphs, which should impact on the energy landscape that we see. And this is what we get out from the simulations. So this is now in a box. It still only contains 2 molecules, but with no other symmetry constraints on it. And we see this similar to the co-crystal, this sort of dual funneled energy landscape. Alpha and beta are not connected until fairly high energy. So they get connected about 40 kilojoules per mole above the lower energy form, alpha. And below that, you get connections to each of these. Okay, so they're more similar in terms of lower energy barrier structures to both alpha and beta below the point at which they meet each other. Okay. What we've done is we wanted to start to look at how do these energy funnels, or this landscape picture we're getting, how does it relate to the interactions that we see when we visualize these structures? So the nice thing about tetraolic acid is it just has these hydrogen bonds. Those are the dominant interactions in these crystal structures. And we really have 2 main motifs. We have these dimers, where you have pairs of molecules linked up to each other by double hydrogen bonds, or these chains, where we have this chain of hydrogen bonds connecting molecules. And so what we did is we characterized all the local minima, so all the branches on this disconnectivity tree according to the hydrogen bonding that you have in the sort of endpoint, the local minimum. And what you see is that there's actually quite a nice correlation between hydrogen bonding motif and the funnel in which a structure sits. So you see that sort of above alpha, everything up till the point where you get up to here has a consistent hydrogen bonding. Hydrogen bonds are not needing to be broken, and that's why energy barriers between these structures are low. Once you get to this point, you need to start breaking hydrogen bonds to get to these other structures. And similarly with beta, you have consistent chains within these structures, but you get to this point and you start to break things, and you get structures which don't sit nicely into either of these categories. And then you get to 40 kilojoules per mole, and those 2 funnels get connected. So it connects that sort of chemistry of the structural chemistry to the energy landscape quite nicely, we think. Again, it gives a very different picture from the typical crystal structure prediction landscape that we're used to looking at, these energy density plots, because these 2 funnels again sit on top of each other in those. So we wouldn't have been able to identify them as different funnels from that plot with density as our structural parameter. And a final system we've been looking at is this TBI molecule. I present this because I know it's been fairly well studied in Liverpool. This was initially studied as a molecule. We're working with Andy Cooper's group in Liverpool looking for porous molecular crystals. We'd done crystal structure prediction, and here's that energy plot of predicted crystal structures and the known polymorphs labeled on that. And we have 5 polymorphs we end up getting for this. And a neat thing about this is that you end up with quite high energy polymorphs, like especially this gamma point. The reason that we see it, or what makes it sort of stand out in this plot, is that we have these spikes of structures which are, for the density at which they sit, these are very low density structures, they have lower energies than you would expect. Okay, so they do stand out a little bit on this energy density landscape, unlike the other systems I've talked about. And this is something now we use, this idea of looking for spikes at low density. And it's helped us find some other interesting new structures. Trimesic acid, we found a new polymorph of this after CSP found another of these low density spikes corresponding to this open structure of trimesic acid, which we published a couple of years ago. This molecule, this pyrene substituted molecule, which we're looking at as a photocatalyst. Again, it has a very low density, which corresponds structure, which we got to experimentally, and has the nicest catalytic properties. And it's one of these low density, high energy spikes. So these seem to be important, but we want to understand them more. And the hypothesis we have, just from looking at this energy density landscape, is that these sort of spikes of structures correspond to deep wells on the energy landscape, which are separated from the dense crystal packing by high energy barriers. And that's why you can take something like this gamma structure at a density of about 0.4, very low density for a molecular crystal, and it can sit on the bench and it's stable. Okay, we have a crystal structure solved from a structure which sat at, I think, 500 Kelvin. Okay, so this is a stable structure, although it's very high energy. So the hypothesis of this high energy barrier, but we wanted to probe this. We did, in the original work where we published this, we did some work to try to understand the stability by taking some of these structures and running molecular dynamics. So allowing the molecules to essentially follow Newton's laws of motion to sample the energy landscape and heating them up to see if they would transform. We used a benchmark to sort of calibrate these types of computational experiments of looking at this T0 molecule, which doesn't have the hydrogen bonds. We took something of a similar density up here. We take that crystal structure from the landscape and we apply molecular dynamics, and very quickly it collapses because there isn't a large energy barrier to stop that collapse to a higher density. Okay, and here across that whole energy landscape, everything that's low density collapses once you heat it up to room temperature. So they are local minima on the landscape only because those predictions are performed without temperature in them. And we did this for other molecules. Most importantly, that T2 molecule, you take the known polymorphs at low density, put them in molecular dynamics, and they stay as they are. They don't collapse to low density or high density. And even at very high temperatures, they stay as they are. Okay, so it hints that there is a large energy barrier, but that's something we wanted to probe now that we have this threshold algorithm in place. So we applied that. It's more complex. We had to do this we wanted to get an accurate picture. So we did this in a P1 unit cell, no other symmetry constraints, 4 independent molecules. And that allows us to capture all 5 of the polymorphs. And this is the picture we get, which is quite nice, I think, in terms of starting to understand the experimental results. We have 4 main energy funnels. So there's this gamma funnel, which is separated from all of the rest by the highest energy barrier, and that's that very low density structure. Alpha and beta sit sort of within the same funnel, and they're connected to each other by a lower energy barrier, and they're most closely connected to the dense form, this epsilon, and delta, which on the energy density plot didn't stand out as one of those spikes, is also in a separate funnel. So this gives us an information that we were missing when we were looking at the results before. Okay, so this is quite nice in terms of characterizing things. It is a bit messy, so you can prune this graph down and just keep the starting structures to get an idea of the energy barriers between them. All right, and now it's a little bit easier to visualize and analyze. An important point here is that when we did those molecular dynamics studies, all of these points, gamma, delta, and epsilon, they stay as they are. They don't transform to anything else. Alpha is the case where you do start to get transformation on a short time scale to the beta form, and that's the pair of crystal structures where you have the lowest energy barrier. So the results from this threshold algorithm are actually aligning quite well with the much more expensive molecular dynamics approach to probing things. And another thing just to mention is that probably the reason why we get those spikes on the energy landscape that we saw before is because density correlates quite nicely with the basins on this energy landscape that we now see from the threshold algorithm. So that gamma set of structures and everything connected to it is at low density. Everything connected to delta is at a similar density to delta. Things connected to alpha and beta are at similar connections, so similar densities. So here you get sort of these basins on the energy landscape at different densities, and that's why we had seen them in those original studies before we had the threshold algorithm. Just the final thing I wanted to talk about is we've now started to look at this a little bit to see, one, is there a way we could do this without the need to energy minimize all of our perturbed structures, because that's actually the most expensive part of things. The reason we need energy minimization is to identify what energy minimum we're in. So we've started to look at whether sort of some of the uses of machine learning methods could help us characterize when a perturbed structure might sit within a certain local minimum. The other reason we've done the work I'm about to talk about is because it's becoming a little bit more common for people to use things like machine learning and unsupervised learning methods to analyze these crystal structure prediction landscapes. So here was a first study we published 3 years ago with Cheriotti's group in Lausanne, where we were looking at pentacene. And what we had was the crystal structure prediction landscape. We apply structural descriptors to all of those predicted crystal structures, and we use some clustering methods to try to find families of crystal structures. So just based on structural descriptors, here we used SOAP, okay, and the clustering we used was HDB scan. And what you found were nice clusters, which the colors on this is we're using dimensionality reduction to reduce this down to 2D just for visualization. And it corresponds to quite nicely, these clusters, to how you would classify these structures if you did it manually, which we essentially did based on the known packing types of polyaromatic hydrocarbons. So these methods that are used in machine learning reproduce sort of heuristic classification that you would get for this type of system. And the picture we have when we do this now, when we've applied it to other systems, is that those structures sit in families and maybe they sit within their own little sub-basins on the energy landscape. Okay, and we wanted to test that by comparing this type of approach to results of the threshold algorithm. So we apply this SOAP descriptor, which essentially captures local environments of each atom within a molecule and then allows comparison of those local environments to give us a structural similarity. Okay, and I go back to both the tetroic acid and TTBI to say the reason we thought this might work out is because here we have correlation between these funnels and hydrogen bonding. Here we have correlation between these funnels and density. So it seems there is a geometrical sort of pattern to these energy funnels, but it doesn't work out very well actually. So we applied this SOAP descriptor to tetroic acid, and here we do PCA of this, and here are the two first principal components and all the crystal structures, and here are the colored points for the alpha and beta basins, and they will overlap each other. So actually these descriptors like SOAP are not capturing the differences between those funnels in the same way that, say, that hydrogen bond analysis did. And again, we can do clustering and cluster things with the SOAP descriptor, but the clusters don't align with the funnels. So actually it seems those geometric clustering methods are giving us different information from the energy barriers we're getting from the threshold algorithm. We did it also for the co-crystal, where we have two very nice basins with lots of structures, so perfect for these unsupervised learning methods. But again, you get overlap in the sort of dimensionally reduced picture of this between the two basins. They're not being separated out. And again, clustering is unsuccessful. So clustering on similarities between SOAP, pairwise similarities of structures, doesn't reproduce the funnels or the clustering that you would get from looking at structures which are related by low energy barriers. And so we've looked at things like distances between pairs of structures within basins and between basins for both the tetroic acid and the co-crystal, and the distributions of those distances just overlap. So you don't have larger distances in terms of geometries of structures between basins as within a basin, and that's why these clustering methods are not able to reproduce what we get from the threshold algorithm. So we're still looking at this to figure out whether we can get some of these machine learning methods to reproduce the sort of classification that we get from those basins that we're seeing. So I'll stop there, and the summary is, I think this threshold algorithm seems to be useful for analyzing molecular crystal structure landscapes. Hopefully it's interesting as well and gives us a different picture of how we see these things. The symmetry constraints that we have to apply do lead to errors in our energy barriers. They will always lead to overestimates of barriers, but we're getting to the point where we can start to lower those, and we're trying to improve the method so that we have to use fewer and fewer constraints. And the final thing is these energy basins don't seem to correlate with what we get from these geometrical descriptors, and that should influence how we think about any clustering we see when we do these geometry-based sort of classification of structures on energy landscapes. Thank the people who fund our work in our group, people who give us time on HPC, and especially Bruce, who's the person who did everything that I've presented today. And hopefully it's been interesting, and I'm happy to answer any questions.
Thank you very much, Graeme. Let's thank Graeme first. Let me stop.